Okay, now look at the example 1 for PI compensator. So given the system in the next figure, operating with damping ratio zeta of 0.174, show that the addition of the ideal integral compensator, PI, shown in figure B, reduce the steady state error to 0 for a step input, meaning that this is type 0, without appreciably affecting transient response. The compensating network is chosen with a pole at origin to increase the system type and a 0 at negative 0.1. This is 0 close to origin for PI compensator. Okay, so the 0 is close to the compensator pole so that the angular contribution of the compensator evaluated at the original dominant second order poles is approximately 0. Thus, the original dominant second order closed loop poles are still approximately on the new root locus. So this is the example, this is the figure A for uncompensated system before we add PI compensator, pole at origin and 0 close to origin. This is the original plan. While in figure B, this is the compensated system. By adding the PI compensator, we place pole at origin as equal to 0 and also 0 close to origin. In this case, 0 is equal to negative 0.1. The original plan is maintained. So we first analyze the uncompensated system and determine the location of the dominant second order poles. Dominant poles are complex poles that is nearest to J omega axis crossing or nearest to the imaginary axis crossing. The nearest the dominant pole to J omega axis crossing, the slower response will be. I repeat, the nearest dominant pole to J omega axis or to imaginary axis, the slower response will be. So this is the closed loop transfer function. So from the block diagram, so find the closed loop transfer function Kg over 1 plus Kg, in this case H is equal to 1 unity feedback. Okay, H is equal to unity feedback. So this is the closed loop transfer function. This is open loop transfer function. This is closed loop transfer function. Okay, in this case, given usually the question will give you the value of gain K, in this case 164.6. So you plug in the value of K in this closed loop transfer function from the open loop transfer function, and then based on the denominator of the transfer function, equate this to 0 to find the closed loop poles. Okay, now we find the closed loop poles. In this case, this is third order, so the first pole is minus 11.61 and the other two is the complex conjugate poles. The complex conjugate poles from the closed loop system is your dominant poles, since this is the closed loop transfer function for the uncompensated system, meaning that this is the uncompensated dominant poles. So we find that the dominant poles are these complex conjugate poles, and we usually choose for the positive imaginary coordinate as our dominant poles. Both are dominant poles, but for our analysis we focus on the positive imaginary roots instead of negative imaginary roots. So our dominant poles is negative 0.6933 plus J 3.926 for a gain K of 164.6. For the same gain as that of the dominant pair K equal to 164.6, we find that the third pole is equal to negative 11.61.